Understanding neuroplasticity, the brain's remarkable adaptability. Neuroplasticity, also known as brain plasticity, refers to the brain's ability to reorganize itself by forming new neural connections throughout life. This dynamic process allows the brain to adapt to new experiences, learn new information, and recover from injuries. Let's delve into the mechanisms of neuroplasticity and the famous adage neurons that fire together, wire together. Mechanisms of neuroplasticity. 1. Synaptic plasticity. Synaptic plasticity involves changes in the strength of connections between neurons, known as synapses. These changes can be either long-term potentiation (LTP). This is the process by which synaptic connections become stronger with frequent activation. It is believed to be a fundamental mechanism underlying learning and memory. Long-term depression (LTD). This is the weakening of synaptic connections when they are less frequently activated. It plays a role in forgetting and in the fine-tuning of neural circuits, too. Structural plasticity. Structural plasticity refers to the brain's ability to physically change its structure in response to learning, experience, or injury. This includes neurogenesis, the process of generating new neurons, which primarily occurs in the hippocampus, a region associated with memory and learning. Dendritic branching. Neurons grow new dendrites, the branch-like extensions that receive signals from other neurons. More dendritic branches can enhance a neuron's ability to form new synapses. Axonal sprouting. Damaged neurons can sprout new axonal projections to reconnect with other neurons. Neurons that fire together, wire together. This phrase, often attributed to Canadian psychologist Donald Hebb, summarizes a key principle of synaptic plasticity. 1. Hebbian theory. Hebb's theory posits that simultaneous activation of cells leads to pronounced increases in synaptic strength between those cells. Essentially, if two neurons frequently activate at the same time, the connection between them strengthens. This principle is encapsulated in the phrase neurons that fire together, wire together, highlighting the idea that synchronized activity can reinforce neural pathways. 2. Mechanisms behind Hebbian learning. Coactivation. When two neurons are repeatedly activated together, chemical signals strengthen the synapse between them. This includes the release of neurotransmitters and growth factors that promote synaptic consolidation. Calcium influx. Frequent activation leads to increased calcium ion concentration in the postsynaptic neuron, which triggers intracellular processes that strengthen the synapse. AMPA and NMDA receptors. These receptors play a crucial role in LTP. NMDA receptors, in particular, allow calcium ions to enter the neuron, initiating pathways that lead to synaptic strengthening. Applications and implications. 1. Learning and memory. Neuroplasticity underlies our ability to learn new skills, form memories, and adapt to new environments. LTP is a critical mechanism in the formation and retention of memories. Repetitive practice and learning activities enhance synaptic strength, illustrating why practice improves performance in various skills. 2. Recovery from brain injury. Following injuries such as stroke or trauma, neuroplasticity enables the brain to compensate for lost functions. Rehabilitation exercises can stimulate the growth of new neural connections, aiding in recovery. Techniques like constraint-induced movement therapy (CIMT) leverage neuroplasticity to improve motor functions by forcing the use of affected limbs. 3. Mental health. Neuroplasticity is also implicated in mental health conditions. For instance, chronic stress can lead to maladaptive changes in the brain, but therapeutic interventions like cognitive behavioral therapy (CBT) can promote beneficial neural rewiring. Antidepressants and other psychiatric medications can enhance neuroplasticity, supporting recovery from mental health disorders. Enhancing neuroplasticity. 1. Physical exercise. Regular physical activity promotes neurogenesis and enhances synaptic plasticity. Exercise increases the production of brain-derived neurotrophic factor BDNF, a protein that supports the growth and survival of neurons. 2. Mental stimulation. Engaging in intellectually stimulating activities such as learning a new language, playing musical instruments, or solving puzzles can enhance synaptic plasticity and cognitive function. 3. Healthy diet. Nutrients like omega-3 fatty acids, antioxidants, and vitamins support brain health and neuroplasticity. A balanced diet rich in these nutrients can aid in maintaining optimal neural function. 4. Mindfulness and meditation. Practices like mindfulness meditation have been shown to increase gray matter density in brain regions associated with learning, memory, and emotional regulation, suggesting a role in enhancing neuroplasticity. Conclusion: neuroplasticity is a fundamental property of the brain that underpins our ability to learn, adapt, and recover. The principle that neurons that wire together highlights the importance of activity-dependent synaptic changes in shaping our neural networks. By understanding and leveraging neuroplasticity, we can foster cognitive health, improve recovery from brain injuries, and enhance our learning capabilities.
Please like and share this video and subscribe to my channel for more life-changing and engaging content.